So today's Chapter 9, Section 2 is going to be a little bit easier actually than Chapter 9, Section 1. Section 2 focuses completely on linear systems of equations. So you're going to have two equations, both of them are going to be linear, and you're going to have two variables in those equations, an x and a y variable. We're going to focus on solving by elimination and solving by graphing. So when you're solving by elimination, I'm going to go over these directions with you as we go. But again, you line up your x's, y's, and constants. If needed, you change one or both of the equations so that you get a pair of opposites so that a variable will cancel out. You solve for the variable that's left over, and once you solve, you plug it back into the original equation, any one of the two, and you find the other variable. So one thing's interesting about lining it up. Normally we do like 3x plus 2y equals 7 and maybe 4x minus 7y equals 5. And we line up our x's, our y's, and our constants. We don't have to have it in standard form with the x and the y on the left and the number on the right. While that's preferred, you could have, for example, 2y equals 7 minus 3x, and you could have negative 7y equals 5 minus 4x. At the end of the day, you're going to get you're going to eliminate the same variable, you're going to multiply and do everything. So don't feel that it has to be in standard form or you can't use elimination. What you want to do is just make sure that you reorder everything so that the like terms are above and below each other. The other issue we're going to have is that when you're solving a system of two linear equations, there's three solution options that you're going to get, okay? And again, this is when you have two linear equations, and which is what we have in this entire section. The first option is one solution. The second option is no solutions. And the third option is infinitely many solutions, right? Or all real numbers, okay? And when you're, remember that solutions are where your two lines or graphs intersect. So when you have one solution, right? A one solution issue is you have two lines and they intersect there. And that XY coordinate is the solution. No solution is when you have parallel lines on the graph. And since they don't intersect, right, they're parallel, they're going to have no solution point. And all real numbers or infinitely many is going to be when you have one line and then a second line goes right on top of that line, and then every point is a solution, okay? So that's what it looks like in a graph. However, algebraically, that could present a problem. You might not notice it. So when you get something like, again, let me give an example. When you get like 2x plus 3x, oh, no, sorry. Let's say you get 2x plus, oh my gosh, sorry, plus 3y equals 10. And then let's say you get minus 2x minus 3y equals 15. And you come over here and you go, okay, let me add and try to eliminate. Okay, I eliminated my x's, but all of a sudden you eliminated your y's and your numbers are 25. So basically 0 equals 25. Now you know that this is a false statement. This is not true. You're not going to get an x equals something or a y equals something. You're going to get a number equals another number, which makes 0 sense. And when you get this false statement, this means no solution. And what that means is those lines were parallel. So algebraically, a no solution shows up as a false statement, okay? Like, again, 0 equals 25 or 10 equals 15 or something like that, okay? The next scenario is the all real numbers. So what might that look like? Well, the all real numbers looks like this. Let's say you have, you do your math, okay? I don't know exactly how we're going to do the math, but when you do the math, you end up with maybe like this. 2x plus 3y equals 10, negative 2x minus 3y equals negative 10. And when you add your columns, you get 0. You get 0 equals 0. Well, guess what? That's a true statement. That's your all real numbers, okay? So when you get a true statement, like 0 equals 0, it's all real numbers. It's basically the same line. So we have to look out for those answers when we start doing the work algebraically. So we're going to start out super easy with this first example. You're going to notice in this first example that the y's are opposites. And so those are the ones, obviously, that I'm just going to add my columns. 8x, the y's get eliminated, equals 16. So x is 2. And then I'm going to choose one of the equations to plug the 2 back into. So again, I always try to pick smart when I do my equations. I try to pick where it's easier. I try to avoid constants or coefficients in front of my variables. If I can't avoid coefficients, at least in this case, I'll avoid the minuses. So I'll plug it into the first equation. So 3 times 2 plus 2y equals 4. 6 plus 2y equals 4. 2y equals negative 2. And y equals negative 1. And I would want it in an ordered pair form, because we want you to recognize that the x and the y go together. That is a unique point on the graph where those two lines intersect. And with regard to the equations, it's the only combination of x and y that will make both statements true. And that's kind of how we can check our answers as well. All right, so now I'm going to go on to the next one. Again, this one's really easy because my y's are opposites. So I'm going to get 4x equals 3, x equals 3/4. And so again, this is not super pleasant because I have a fraction. I have to plug my fraction into one of these equations. Since I have to plug the x in and x is a fraction, I'm going to try to plug it into an equation where this denominator works well with the coefficient. Maybe something gets canceled out. And I noticed that both of them would work. So I'm going to focus on the top one. And the reason I chose the top one is because that way I don't deal with negatives. So 2 times x plus y equals 4. When I simplify this, I get 3/2 plus y equals 4. And y equals 4 minus 3/2. Well, 4 is the same as 4 is the same as 8/2. I don't know why it took me so long to find that. 8/2 minus 3/2. Wow, what a mess I'm making there. Sorry, guys. Let me try this one more time. So 4 minus 3/2 is the same as 8/2 minus 3/2, which is 5/2. So my ordered pair for my solution is x is 3/4 and y is 5/2. You can write it as a fraction. Improper fraction is totally fine. If you want to write it as a mixed number, that's fine too. So that would be 2.5. Okay? We keep going. Now, when I get to number 3, I realize there's no opposites just yet. So I'm going to have to do something to the equations to make one an opposite of the other. And I think the bottom one is going to be the easiest one. If I multiply it by 4, I'll very easily get an opposite. I'm going to get 20x plus 4y equals negative 4. So I'm not going to use that one for now. And I'm now ready to add my columns. I'm going to get 22x. My y's cancel, and I'm going to get negative 11. So I'm going to divide by 22, and I'm going to get x equals negative 1/2. And again, I have my first value in my ordered pair. X is negative 1/2. Now I need to find the y. So again, I'm going to ask myself, where would I rather plug this x in? Would I rather plug it into here and multiply negative 1/2 by 5 and get another fraction? Or would I rather plug it in here where the 2 and the denominator of 2 will cancel out? Obviously, I'm going to rather plug it into there. So I'm going to do 2 times negative 1/2 minus 4y equals negative 7. Negative 1 minus 4y equals negative 7. Negative 4y equals negative 6. And when I divide by negative 4, I'm going to get y equals 3/2. Okay? And so now I have my y value. So my ordered pair is negative a half, positive 3 over 2. And again, you can leave it like that. And then last but not least, this last one, and again, I see that the bottom is the easiest one for me to work with. I can multiply the bottom by 3, and that's going to give me 15x minus 3y equals 51. Cancel it out. And then when I add my columns, I'm going to get 17x, my y's cancel, equals 68. When I divide both sides by 17, I'm going to get x equals 4. So I have the first answer for my ordered pair. Now I have to figure out where am I going to plug the 4 into. And again, you know me, I'm going to avoid negatives. So I feel like that might be the one I'm going to do. Actually, you know what? I'm not going to do that one. If I look at it a little bit better, I think I'd rather do the bottom one. And again, it's not going to matter. I'm going to get the same answer either way. But since I'm looking for y, I don't have to do anything with the 3. I think that's going to be a little bit too busy. So I'm going to use the bottom one. 5 times 4 minus y equals 17. 20 minus y is 17. Negative y equals negative 3, which means that y equals 3. So here's my two values, but again, I want them as an ordered pair. And so that's the first page. Very basic, two linear equations in a system, easy to solve. All of these had one solution. So we keep going now to the next page, and they're going to start to get a little more challenging, right? One of the challenges is in this, for example, example 5, you're going to see that there's no place here, like there's no opposites, and I can't just multiply something to one and not the other. So I personally like to get rid of the x's. I like to get rid of the y's rather and be left with my x's. So I often choose to multiply the top and bottom to where my y's will eliminate. It doesn't have to be that way, but that's just my method. So if I multiply the top by 4 and the bottom by 3, I'm going to get positive and negative 12y, which will cancel out. So that's how I'm going to go about it. So I'm going to come over here. I'm going to get 20x plus 12y equals 36. And I'm going to get 6x minus 12y equals 42. And I'm going to add my columns. I'm going to get 26x equals 78. And when I divide by 26, I'm going to get that x is 3. Now I'm going to pick one of the two equations to plug it into, and I'm going to pick the first one. The reason I'm picking the top one, honestly, is because there's no minuses in it. So I've got 5 times 3 plus 3y equals 9. 15 plus 3y is 9. 3y equals negative 6, and y equals negative 2. So my solution here is 3, negative 2. And there you go. One solution again. In the second one, I'm looking at it, and again, you know me, I'm going for the y's. And so I know if I multiply the top by minus 5 and the bottom by positive 2, I'm going to be able to get what I need here. So my top is going to be minus 15x minus 10y equals negative 35. And over here I've got 4x plus 10y equals 2. When I add my columns, I'm going to get minus 11x equals minus 33. X is 3. When I go to plug it in, I could really plug it into either one. It doesn't really matter. I think I'm going to go with the top one. So 3 times 3 plus 2y equals 7. 9 plus 2y equals 7. 2y equals negative 2. And y equals negative 1. So 3, negative 1 is my solution. So all of these are still one solution. We haven't gotten to a no solution or an infinitely many. I'm sure it's to come. When we get to a number 7, guys, this is again a challenging question because of the decimals. So my suggestion to you guys, I'm not really thinking about opposites and canceling, eliminating variables right now. What I'm thinking I'm going to do is I'm going to want to get rid of the decimals. And so I know if I multiply the top by 100 and the bottom by 100, that's going to shift my decimals 2 places to the right, which is going to leave me with 2x minus 5y equals negative 38. And this is going to leave me with 3x plus 4y equals 104. Now that I'm here, I can sort of start thinking in my head about canceling, right? So what I think I'm going to do here now is I'm going to make my y's opposite. And so I'm going to multiply the top by 4 and the bottom by 5. And so I'm going to kind of do those. I'm going to move these over to here. So I'm going to start with the top one. And I'm going to get 8x minus 20y equals, I think, wait, 38 times 4. Let's do this right. 32, carry the 3, 15. So it's going to be 152. Okay, so that's that one. And it's going to be negative. Let me fix that. It's going to be negative 152. When I do the bottom one, I'm going to get 15x plus 20y equals, and I'm going to get 520. When I add my columns, I'm going to get 23x equals, and I'm going to do 520 minus 152. And I'm going to get equals 368. And when I divide 368 by 23, I'm going to get x is 16. So I got my first answer, and I have to plug it into one of these. I'm thinking, even though I like to avoid negatives, I feel like the numbers are going to be smaller in the first one. I'm not sure. I don't know. Maybe I will do the bottom one. So I'm going to do 3 times 16 plus 4y equals 104. And I did it to avoid the negatives. 48 plus 4y equals 104. 4y equals 104 minus 48, which is 56. And y equals 14. So 16, 14 is my solution. Again, one solution. So notice I use the double multiplication process for elimination, and that's fine. Again, anything that makes my work easier or efficient is going to be what I choose to do. When I get here to number 8, again, I'm looking for opposites, and I see that if I just multiply the top equation by 2, my y's will become opposites of each other. So 2x minus 4y equals 6, and negative 2x plus 4y equals 1. And when I go to do this, I didn't notice it before, but by multiplying by 2, I made both of my x and my variables opposites. So I get 0 equals 7. And guess what? That is a false statement. And so because this is a false statement, this is a no solution. Okay, so that's the answer here. The answer isn't false statement. The answer is no solution. And what this means, guys, is that these two lines are parallel to each other. Okay, so we're going to get to a few more examples on this page. So again, here we've got, when we look at this first equation, I'm looking at it and I see that, again, you all know, it's a pattern with me already. I kind of always hone in on the y's. So when I come over to here, I notice that if I multiply the top by 2, not both of them, if I multiply the top one by 2, my y's are going to be opposites. So I'm going to get 12x minus 10y equals 6. And again, I notice, oh wow, I start canceling other things as well, right? So both variables were eliminated. So 0 equals 11. Again, that's a false statement. And so the solution here is that there's no solution. So this is the answer I would want, okay? And again, that means parallel lines. Again, I'm going to go to number 10, and quickly I'm going to look at it, and I see that if I multiply the top by negative 2, my y's will cancel. So I'm going to do that. So I've got negative 4x plus 2y equals negative 2. And then I add, that canceled, my y's canceled, and my constants canceled. And I got 0 equals 0. And this is a true statement. And this is an example of, and I don't care how you write it, you can either do infinitely many solutions, that's one way of doing it, okay? Or you can say all real solutions, okay? Either one is valid. What's not valid is just saying true, okay? True's not an answer. True leads you to the answer, which is infinitely many or all real solutions. And again, what kind of lines are these? These two things, these two equations rather, They represent the same line. It's one line on top of the other, and that's why we got that solution. And then the last example we've got going on, I think it's our last, oh no, we still have a couple more slides. But the last example on this page has a fraction. And so fractions are pretty interesting. You can work them as fractions, and that's fine. You could, but for me, I want to eliminate at all times fractions. So I'm not even worried about eliminating a variable yet. I'm just going to get rid of the fraction. And if I multiply by the least common denominator, which is 8, I'm going to be able to eliminate every denominator here. And so when I multiply a half by 8, I'm going to get positive 4x. When I multiply 1/8 by 8, I'm going to get 1y. And when I multiply negative 3/8 by 8, I'm going to get negative 3. These are going to cancel out every time, okay? And so now I'm going to do my like terms, and I'm going to get 0 plus 0 equals 0. So again, I got this. Again, it's a true statement. And so my solution is infinitely many solutions or all real solutions. Okay, either one of these two is adequate. And again, that means that these two are the same line. Okay. So the last part of this lesson is solving systems by graphing. And again, we are not going to ask you very often to graph, to solve. We're definitely not going to ask you to graph quadratics and conics, circles, all that stuff. We may ask you to solve on this assessment, potentially to solve by graphing on these linear systems, because lines are so easy to graph. So that might be the only type of question we ask you, but you want to know how to do it. I mean, really, nobody in the real world solves by graphing, but solving by graphing is nice because it allows you to see what a solution really means. If you look at this picture, this dot right here where these two lines intersect, that's our solution. That XY combination is the solution to the system. So it's kind of cool to see it. The problem is with graphing is that unless your XY are integers, right? Like this case, 4 and -1, that's great. But what happens if your line intersects over here? Like, what is that order, that ordered pair there? It's, it's some number between -2 and 3 for X and 2 and 3 for Y, but you're never going to be able to figure out that number by graphing. And so graphing is just inefficient. It's an inefficient method, ineffective really, but we're going to give you ones with obviously clear answers just so you can practice the idea of graphing. So I'm going to go over just with the graphing a couple examples of how we might graph. The most common way, the most popular in my opinion, and the easiest way to graph is to graph using slope-intercept form, where you basically take the equation and you solve for y. And when you do that, the m value is your slope and the b value is your y-intercept. And so it allows you to very quickly graph your y-intercept and graph other points using the slope. So if I take each of these equations and I do that, right, I'm going to make, let's say this is my blue equation. I'm going to do 2x minus 3y equals 3, minus 3y equals -2x plus 3, and y equals -2 thirds x, -2 over -3x plus 3 over -3. And again, lastly, I'm going to simplify a little bit. This is 2/3 x, and this is -1, okay? And so what I see here is that my y-intercept is -1. So there's my first point, and my slope is 2 over 3. Remember, your slope is rise over run. So I'm going to go up 2 and 3 to the right, up 2 and 3 to the right. I could also go down 2 and 3 left, down 2 and 3 left. And once I do enough of those dots and I connect them, here is the equation of my line. This is the line of 2x minus 3y equals 3, okay? Then I do the same thing for the, let's say the red equation, right? So I'm going to come over to here, and I'm going to do minus 4x plus 6y equals 6, 6y equals 4x plus 6, and y equals 4/6 x plus 6 over 6, y equals 2/3 x plus 1. So again, I come here, and my y-intercept for my red graph is positive 1, and notice it has the same slope. I'm going to go up 2 and 3 over, up 2 and 3 over, up 2 and 3 over, or down 2 and 3 back, down 2 and 3 back. And when I do enough of those, I connect those lines. And where those two graphs intersect, those are my solutions. Well, guess what? They don't intersect. My lines are parallel. Again, as you get practice, when the slopes are the same, it's either the same line or parallel lines. If the intercepts are different, they're parallel. If the intercepts are the same, then it's the same line. So I kind of knew already, but again, you got to graph this way, and that's how we graph using slope-intercept form, okay? The second way you can graph, which is not my favorite, but I'm going to do it in the next problem just so you have an example of it. And what we do is we graph, so here, let me just go back and just say, here we graphed using slope-intercept form, okay? And here we're going to graph using intercepts. And what I mean by intercepts is x and y intercepts. And so I'll show you this method. You'll probably remember it. What you do is you take one equation and first you make the x 0 and you solve for y. That cancels. Minus 3y equals 3. So y equals -1. So you get one intercept here. When x is 0, y is -1. So right here, you have your first intercept. That's your y-intercept. Then I take the same equation, 2x plus 3y equals 3, and now I make the y equal to 0, so I can find the x. So 2x equals 3, and x equals 3 over 2. So again, when x is 3 over 2, y is 0. So I come over to here, 3 over 2 is 1.5. And so there's my two intercepts, and then all I do is connect my dots. Draw a line through them. Not the best line, but that's it. Okay? So that's another way of doing this problem. I don't know why my graph is so skinny. Let me do that again. There we go. So I graph using intercepts. I find those 2 points. Now I'm going to do the same thing for the red equation. Okay? So for the red one again, I've got x plus 2y equals 5. So I'll make x equal to 0, and I'll solve for y. So 2y is 5, so y is 5 over 2. So when x is 0, y is 5 over 2, which is 2.5. So x is 0, y is 2.5. And then I'll do the next one. So x plus 2y equals 5. Now I'll make the y equal to 0, and equals 5, and x equals 5. So when x is 5, y is 0. Or when y is 0, x is 5. So 1, 2, 3, 4, 5, 0 here. And then now I kind of do it like that. My line is terrible, which is awful because now I did this terrible line. And now guess what? My intercept, I have to figure out what it is. Now I drew this line so badly, I'm not 100% sure that that is really accurate, okay? And I find with this form, I don't think I have as much accuracy. I'd rather have more dots along the way so I could kind of follow a little bit better my path, right? So whatever that dot is, that's the solution to this problem, even though I'm not even sure what it is. And that's why this whole method is really ineffective, if you ask me. If I could solve it mathematically and try to see, right? Let me go back and kind of do it algebraically just to kind of see where the solution should have been. Let me do like -2. So I'm going to do minus 2x minus 4y equals -10. When I add my two equations, I'm going to get minus 7y equals -7. Y is 1. So, okay, right there. And then let me plug that in. So let me do like x plus 2 times 1 equals 5. X equals 3. So 3, 1 is the solution. And look how terrible my graph is, really. It's kind of terrible to say this, but it should be here. That's how off my graph is. So again, if I had drawn this better, they would have intersected at 3, 1. But because I did such a horrible job with my lines, let me kind of go back and do this a little better for you guys. But again, so that's the hardship and the challenge. You saw how fast I solved it using the equations. You know, why would I bother even trying to graph this, right? So let me just 0, -1, kind of go here. And I'm going to try to make sure that I cross that point that I know now it goes through. Okay, that's a little better. Okay. And then let me get the red one again. You can fast forward this video if you don't want to do all this. 1, 2, 3, 4, 5, 0 here. And then the other one was, what was it? It was 5, 0 and 0, 2.5. So 0, 2.5 right here. And I'm going to try to be better here. And there we go. And there's my intersection. Okay. And so that's it. But again, you see the limitations with this. For me, I think slope-intercept form is going to give me the most accurate. So again, they intersect here. So 3, 1 is my solution. Okay. And then lastly, I'm going to do this last one. And this one, I'm going to just go back and do it using slope-intercept. I think that's going to be the best way. So I'll start with that one. 2x minus 3y equals 3, minus 3y equals -2x plus 3, and y equals 2/3 x minus 1. So I got that one. Is that the same equation every time? Oh, I think it's the same example. Oh, it's almost the same as the first example, actually. Okay, so again, I'm going to start at -1, and my slope is 2/3. So up 2 over 3, up 2 over 3, up 2 over 3, down 2, back 3, down 2, back 3. And I feel like the more dots I do, at least for me, who clearly am challenged with these lines, it helps me do the most accurate line I can do, okay? And then I go to the last example here, and I'm going to do this one. And I'm going to do -4x plus 6y equals -6. 6y equals 4x minus 6. Y equals 4/6 x minus 1. So y equals 2/3 x minus 1. So if you notice, guys, when I rewrote it, notice that the equations are exactly the same. My y-intercept is -1 and my slope is 2/3. All my points are going to overlap. This ends up being an example of infinitely many solutions. Infinitely many solutions, or all real solutions. And the reason that it is because it's the same line. So we just drew an example of no solution, all solutions, or one solution, okay? And so this again is what you're going to, if you see a graph on the assessment, it's going to be linear and it's going to be one of these three options.